Guten Tag! Most of the semester will be spent writing down Newton's second law and solving it. That's really the program from here on out for just about everything we do. And it's nice to know going in when Newton's laws are actually applicable, because the range of, or the scope of their validity is limited. And in order to understand that, we have to introduce this notion of an inertial frame, which is a rather abstract concept, but you're totally capable of grasping it. And it is something you want to keep in mind as you go through the semester, because we may have occasion to look at some problems where technically Newton's second law would not be valid, and we can't really do that without an understanding of what an inertial frame is. So first, let me clear up a difficulty with the language here. If you hear me use the phrase an inertial frame, this is what I'm saying here. It kind of sounds like I'm saying uninertial frame. No. If I say an inertial frame, I'm saying this, not something that's not an inertial frame. So let's agree not to use that word. If I would like to refer to a frame of reference that is not inertial, I'll say non-inertial. Okay? So if you hear me say an inertial, I'm saying this. How about we consider a rocket? This is SpaceX's Starship rocket here. It's an actual picture, I think, or artist's rendering. It's tough to tell because it's made out of stainless steel, so it almost looks fake. And let's say that it's moving with constant velocity over the ground. So VRG would be the velocity of this rocket with respect to the ground. Up here, I've said ground frame. I'm talking about the frame of reference attached to the ground. I have not actually drawn a set of axes, but you can imagine an origin at some fixed place on the ground with an X, Y, and Z axis coming out of it. And in this picture, those axes are not going to move. So the length of this arrow represents how fast the rocket is moving over the ground. That length is not going to change, and the direction of that arrow will not change. So that's what's called a constant velocity. So here's our first example of an inertial frame of reference. It's actually an approximation, and I'll explain later why it's just an approximation. But the person inside this rocket, they exist in a very close approximation to an inertial frame of reference, because they're in a vessel that's moving in one direction at constant speed. They're not speeding up, they're not slowing down, they're not turning. That's basically an inertial frame of reference. And let's suppose that they've got a ball in their hand that they throw straight up from their perspective. So they throw it up so that it's moving vertically with respect to their body from their perspective. And never mind about the fact that it would hit the roof of their rocket. Let's just imagine it's free to move up and down. And it might trace out a trajectory like this as the rocket moves forward. So we've already talked about the fact that projectiles move in parabolas if you can ignore air drag and any other force except gravity. So I've just shown you what the trajectory of the ball would look like as seen by somebody standing on the ground here next to one of these trees. Now, why doesn't it just go straight up and then come back down? Well, we talked about the fact that the ball was already moving with the person, so the ball shared this velocity. And the horizontal velocity of that ball doesn't just disappear all of a sudden because it's left the person's hand. So the ball will continue to move forward with the same velocity as the ship, but it's also been given this vertical velocity by the person's throw. Gravity then begins to change that vertical velocity. So you'll notice that the ball reconnects with the person's hand when it comes back down, because again, there should be no change in the horizontal velocity of the ball, because gravity doesn't point horizontally and we're pretending that there's no air drag. So that's what it looks like from the perspective of somebody standing on the ground outside the rocket ship. What would it look like from inside the ship, though? And before we get to that, imagine a set of axes that are fixed to the ship. So they move with the ship. These three axes are anchored to some point on the ship. And yeah, so we're still looking at things from the perspective of the ground, but now you can imagine that those axes are translating through space with the ship. That's that moving reference frame. So the axes that you see here that are moving through space, Those axes constitute the inertial frame which is moving through space. Yes, it's moving, but the origin here is not speeding up, it's not slowing down, the origin is not moving along a curved path, and these axes are not rotating. See how they maintain their orientation as they move through space. Okay, now let's look at things from the perspective of the person on the rocket. So I will refer to that as the rocket frame. It is an inertial frame of reference for the reasons I just mentioned. The rocket is moving in a straight line at constant speed, not turning. And this is what things might look like from the perspective of somebody inside. Notice that I've now indicated that the ground is moving past the rocket in the opposite direction. Velocity of the ground with respect to the rocket. And there it is. So the ground is whizzing past to the left, and from the perspective of the person in the rocket, the ball really does just appear to rise and fall. Let me do that again. That's what you would expect to see from inside the rocket. Again, forget about the fact that the ball would hit the ceiling. You wouldn't expect to see the ball move right or left, just up and down, because the person within the rocket threw it directly up from their perspective. So this moving reference frame that I've just illustrated here with the slides, that is an inertial frame of reference because the rocket is not turning, it's not speeding up, and it's not slowing down. Now what do I have here? Yeah, same thing. This time I've stuck the axes back on the ship, and you can see how the axes are not moving. Do you see how you could assign coordinates to the location of the ball for each of these slides? And you'll notice that the x-coordinate of the ball, which is how far it is right or left, that x-coordinate's not changing, and the z-coordinate is not changing. See how the z-axis is coming out of the page there? The z-coordinate and the x-coordinate do not change. Only the y-coordinate is changing during the ball's motion. Why is that? Because the only force present is gravity. So if there really is no other force acting, there's no reason that the ball should be accelerated left or right. Nothing is pushing on it to the left or to the right. So one way of thinking about an inertial frame is it's a reference frame in which things behave the way you expect them to. Meaning, if you don't see a force acting on an object, then there's no reason that the object should be accelerating. If there's no force horizontally, you should see no acceleration horizontally. And that's what we're observing here. So even though the rocket is moving, because it's moving at constant speed, we don't observe this ball accelerating left or right. Now it does accelerate up and down, but that's because of an observable force. That's because of the presence of gravity. Okay, let's make things a little more complicated now. Suppose the rocket turns on its thrusters, and so it's ejecting fuel backwards, and that gives the rocket a thrust forwards. We'll talk a lot more about that when we get to momentum later in the semester. There's an exchange of momentum between the rocket and the ejected fuel. But that thrust amounts to an acceleration of the rocket in the forward direction. So not only is the rocket moving to the right over the ground, it's also picking up speed. And now this has become a non-inertial frame of reference. Yes, it's moving in a straight line, but the axes that I fixed to the rocket, they are now speeding up. So that is a non-inertial frame. And we're going to see that that results in perhaps some surprising motion of the ball. The ball will appear to be accelerating in a surprising way, or not surprising way, depending on whether you've thought about this before or not. So what happens now if the person in the rocket throws the ball straight up from their perspective? What will the trajectory of the ball look like as seen by somebody, again, in the ground frame, just standing here on the grass? Well, they still see a parabola. Yes, the rocket is accelerating, but the ball does not need to accelerate with the rocket because once it's been thrown, the only force acting on it is gravity. Again, forget about the ceiling of the rocket. Once this person releases the ball, they're not pushing on it anymore. Nothing else in the rocket is pushing on it. Only gravity is acting on the ball. So we would expect the ball to move along the same parabola that it would normally as seen by somebody on the ground. But check it out. It no longer reconnects with the person's hand because the ball kept moving horizontally at the speed the rocket had when the person released the ball. whatever speed this ball was moving horizontally when it was released, it keeps moving horizontally at that speed, and then it's got the additional change in its y velocity due to gravity. The rocket, on the other hand, is increasing its speed, and so the ball does not catch up with the person's hand. The person overtakes the ball horizontally. What's that going to look like from within the rocket ship? So now we're back in the rocket frame, and the ground appears to be moving to the left past the rocket. Not only that, the ground appears to be picking up speed with respect to the rocket. So I put AG for acceleration of the ground. And I should really point out there is an asymmetry here because the rocket really is the one doing the accelerating, not the ground. And so the ground is still close to an inertial frame. The rocket is no longer an inertial frame. But we can still, from the perspective of the rocket, we can still regard the ground as accelerating to the left because it's moving off to the left and it appears to be moving faster. So what does the trajectory of the ball look like? Can you guess first before I show you my interpretation? It should look something like this. Not only is the ball rising and falling, it appears to be flying off to the left as seen by the person on the rocket. So suppose that you on this rocket ship didn't actually realize that you were picking up speed. Now that's silly because we feel the acceleration of a vehicle. If you're in a car that's picking up speed, you feel it. There's forces within your body, between your seat and your back, etc., that you can actually sense. But suppose you had no way of knowing that. You might be surprised to see, this ball not only rise and fall, because remember, you tried to throw it straight up, but for some reason, in addition to rising and falling, it's flying off to the left. That would be surprising to you if you thought you were in a rocket ship that was, let's say, parked on the ground or moving forward at constant speed. This goes back to the discussion about a passenger jet. If the stewardess, or what's the politically correct term nowadays, if you're on an airplane and somebody brings you the complimentary can of soda and a cup with ice in it, when you pour out the soda into the ice, you don't expect the soda to fly past the cup and spill all over your shirt unless the airplane is currently taking off or speeding up rapidly or experiencing turbulence. If the airplane is moving in a straight line at constant speed, then you might as well be parked. You can safely pour out that drink. That's not what's happening here. The rocket ship is speeding up. And so it almost appears as if there's some invisible force accelerating this ball to the left. There is no force doing that. We know that it's really a consequence. It's almost like an illusion. I shouldn't say illusion, but it appears to be doing that because the rocket is actually accelerating. So the rocket is a non-inertial frame in this instance. It's not just moving in a straight line at constant speed. It's speeding up. And as a result, we see the appearance of so-called fictitious forces. If you were inside this rocket ship, your brain, or your imagination might tell you that something is pushing this ball to the left in order to get it to trace out that trajectory. And I don't want to call it a parabola because I don't think it's actually a parabola. It wouldn't be difficult to figure that out mathematically, what the actual shape of that curve is, but I do not believe it's a parabola. Okay, so what's the difference between the inertial frame, which was the first example, and the non-inertial frame, which is this example? Acceleration. If that rocket ship is picking up speed, or we're going to see if it's turning, those would constitute non-inertial frames, and as a result, you see unexpected motion. You see the ball deflect in a way that you can't obviously explain because you don't, it's not like there's a wind inside the rocket that appears to be blowing the ball backwards. You would see that and think, that's peculiar. I expected the ball to just go straight up and straight down under the influence of gravity. Why is it going backwards? It's because you're in a non-inertial frame, a frame of reference that's being accelerated. And now we arrive at the law of inertia, also known as Newton's first law. It's the one that says an object at rest will continue at rest, an object in motion will continue moving in a straight line at constant speed unless a force is impressed upon it. I don't know the actual wording that Newton used. In fact, he probably wrote it down in Latin. The modern statement is probably clearer than the way Newton first wrote it, but I've mentioned this before. My theory about why the law of inertia is not at all surprising to most people living in modern times is because we've all seen. I've caught this guy in a compromising frame there. We've all seen things like air hockey tables and bowling balls and fast-moving baseballs. Some of us have flown in airplanes. Most of us have ridden in cars or buses. So we have plenty of direct evidence that unless things are forcibly brought to a stop, they tend to just keep going. Right? The bowling ball, because there's very little friction between the ball and the lane, it just keeps going until it hits the pins at the end. And a baseball moving really fast tends to keep going, but we sense that it's the air that slows it down. Why do we sense that? I suppose because if you've ridden in a vehicle and stuck your arm out the window when you're going fairly quickly, 50 miles an hour, you feel the air drag. So I pulled up a video of the largest air hockey table I could find. This just popped up in June of this year, I think. So these guys built, I think they said it was a 10 meter. That's probably too long. It's a very large air hockey table, and they're a little overly enthusiastic here. But let's take a little clip from this and observe the motion of the puck.
Oh, okay. Final minutes. Oh, Jamie! Micah Salvatore!
Did you see that? Let's go back a few seconds. Watch the trajectory of the puck. I could even do it in slow motion here. Can I do that? Playback. Let's go with quarter speed, or 1/2 speed. That ought to do it.
Oh! Okay. Final minutes. Oh, Jamie! Micah Salvatore!
It sure looked like a straight line, did it not? Why not go the extra mile and take that video clip, throw it into Tracker, and see if we can confirm that the velocity is in fact a constant? So here we are in Tracker, and I've ripped a clip from YouTube using some software I downloaded for that purpose. And one thing I'm noting here is that the camera view is not really overhead. And that means that the plane of the motion is not perpendicular to the line of sight. If I set up X and Y axes, the camera is not really looking at the motion along the X and Y axes. So I expect that to introduce some error into the analysis here. But first I will grab the relevant frames. Let's see here. So right here is when it's left his, I don't know what you call this thing. Okay. That ought to do it. I'm not even going to mess with adjusting the frame rate because I don't care about the sense of distance. I just want to see if the slope of position versus time is a constant, because we know that the slope of position versus time is velocity. And I will line up the axes here with the edge of the table. That looks good enough. Create a point mass. And I attempted to do this with Auto Tracker. I was not successful because of the pixelation and these red lines here. So I'll just do this I'll just do this manually. It shouldn't be too difficult. Let me zoom in here. And I believe you hold down Shift. Yeah, so I'll just click at the center of the puck and it automatically advances to the next frame. Oh, there's those darn sticky keys again. So far, it's looking good. I see roughly constant slope off to the right there. Are you finding this therapeutic the way I am? Okay, it looks like I've grabbed all the frames, and I'm sure you see a little bit of curvature in this graph the way I do. Right click, analyze. You know what? I just remembered you don't actually see this other window, do you? Okay, so I'm going to skip that part, but I can enlarge this here. And the slope really doesn't look totally constant. So remember, this is not an actual picture of the trajectory. That's not the path in space. This is the x-coordinate in time. And if the puck really is moving with constant velocity, that means both components of velocity would be constant, including the x component, we would expect the slope to be constant. But it looks to me like it's actually slowing down a little bit. Now, that may not have to do with the camera angle. I would really need to think about the projection of those coordinates mathematically. That sounds kind of challenging. It could just be air drag. Maybe that puck is slowing down just a little bit because of air drag. It's supposed to be levitating on that little cushion of air, but it's impossible to eliminate air drag altogether. But this is pretty good evidence for the law of inertia, which is really Newton's first law. And that says that if there's nothing pushing or pulling on the puck, it should just continue moving in a straight line at constant speed. We may as well check the other coordinate. Let's look at a graph of y-coordinate versus time. All right, it's a little jagged there, but that's probably because I was kind of sloppy with my tracking there, with my clicking. Okay, if air hockey had existed 2,000 years ago, I think Archimedes would have come to, no, not Archimedes. He was the more mathematically inclined. Aristotle would have come to different conclusions. I think Aristotle was the one, renowned philosopher, a little confused about physical ideas. He thought that when you shoot an arrow from a bow, the arrow continues moving because the air is closing behind it and like squeezing the back, the fletching on the arrow. And that the reason the arrow returns to the earth, in other words, falls, is because it's made from materials in the earth and it wants to be back. I don't know. They were very primitive notions compared to the understanding that we have now. But if I'm saying that if they had access to air hockey and vehicles and baseball and bowling, things like that back then, people would have come to very different conclusions much earlier. Moving on in our discussion, let's simplify things a little bit and get rid of gravity. Because with gravity, we have to think about parabolas instead of straight lines. Suppose we're way out in space, far from the Earth, far from any gravitating body. Of course, that's impossible because the reach of gravity is infinite, but you can at least get pretty far where the influence of gravity is much smaller than it is here at the surface. And suppose we've got a cannon way out there in space, and the cannon is made for launching, you guessed it, kitty cats. So here's a kitten that's been launched in a safe way, no harm to the cat, and it's moving in a straight line at constant speed, as you would expect it to do. Really, it's the cat's center of mass, which is moving in a straight line at constant speed, because you would expect the cat to be twisting around anyway to get its bearing. And we need somebody to be observing this, otherwise there's no discussion. So for reasons I can't explain, I chose to go with Condoleezza Rice, former Secretary of State. I believe that was her position. Also known as Condi Rice. This is probably before your time. So I've put her behind her desk, and she's in a see-through box way out in space, and this box constitutes an inertial frame of reference because it doesn't have a rocket engine on it. She's not turning, twisting. She, inside the box, is just moving in a straight line at constant speed. So VCS, that would be the velocity of Condoleezza, with respect to space. So I'm imagining, instead of like the ground, which we had previously with the starship, just imagine there's a fixed set of axes. Maybe they're fixed to the cannon. I'll call that the space frame. Condoleezza is in her own little reference frame moving through space. So this is the velocity of Condi with respect to the space frame. And again, the length of the arrow would represent her speed, and that's not going to change. So try to imagine what the trajectory of the cat would look like as seen from Condoleezza's frame of reference. Here it is. Those are her axes. Those are going to move with her. So that's Condi's frame of reference. That's an inertial frame because the axes are not twisting. The origin's not turning, and it's not speeding up or slowing down. So here it is. She's moving to the right while the cat moves up. So with respect to the space frame, the cat is moving in a straight line, constant speed, and Condi is also moving in a straight line, constant speed. Different directions, of course, and different speeds as well. Let me go back again. Try to imagine what the trajectory looks like from her perspective. If you were sitting at that desk and you think of yourself as being at the origin of the universe, you're the center of the universe, what's the direction and speed of that cat with respect to you? Well, here's how I think about it. Since we know that the cat moves off to the left from her perspective, let's put her on the right and watch what happens. This is now from Condoleezza's frame, which is an inertial frame. Okay, I'll do that again. So obviously the direction of the cat appears to have changed, and the speed as well. And down here I'm indicating velocity of space with respect to Condi. So if she's moving to the right through space, you can think of space as moving to the left with respect to her, or the cannon is moving to the left with respect to her. And the whole point here is that, yes, the cat's speed and direction appear to have changed, but what is still true about this cat? Condoleezza doesn't observe any force on this cat because we're out far away from any planet or star, so we don't expect there to be a gravitational field. There's no wind. Nothing's pushing or pulling on that cat. And as a result, the cat appears to follow a straight line trajectory at constant speed. That's the law of inertia. So the velocity vector may be different, but it's still a constant velocity. And in that sense, there's a symmetry between the two reference frames. It doesn't matter if you're in the space frame attached to the cannon, or if you're in Condoleezza's moving frame of reference. The law of inertia is obeyed either way. So which of these reference frames is the correct one, if that's even a sensible question to ask? Like, is Condi really the one who's moving and the cannon is at rest? Or is Condoleezza at rest and the cannon is moving with respect to Condoleezza? You can look at it either way. The idea is that there's really no absolute reference frame. I mean, where is this cannon anyway? I just made it up. So you may be thinking, okay, fine, if the Earth is not an absolute reference frame because the Earth is going around the sun, maybe you could take these X, Y, and Z axes and attach them to the sun. And that really would be the frame of reference that's not moving. But most of you know that the sun is also moving. The sun makes a giant orbit every 240 million years, something like that, around the center of the galaxy. It's a much bigger orbit, but the sun is definitely in motion. Then maybe you think, go to the center of the galaxy, and that's your absolute rest frame. But the galaxy is moving towards the Andromeda galaxy. And then both of those galaxies are moving around the center of mass of some much larger cluster of galaxies. So as you zoom out, so to speak, you just can't find an anchor point. There's no point in the universe, to our knowledge, that's not moving with respect to anything else. But there is a special type of reference frame which we're already talking about. It's called an inertial frame of reference. So both of these frames, while not being absolute frames, because what is that? They are inertial frames. How do I know? Because the cat, which was launched from the cannon and has no force acting on it, that cat moves in a straight line at constant speed from either frame, or as seen in either frame of reference. So that's really the definition of an inertial frame. What is an inertial frame? It's one in which Newton's first law holds true. Newton's first law says if an object has no forces on it, it will continue moving with constant velocity. That means it either stays at rest or it continues in a straight line at constant speed. If it does something else, if there's no forces on it and it's deflecting for some invisible reason or by some invisible hand, then that tells you are not in an inertial frame of reference. So I didn't include these slides, but you can imagine, what if we did stick a rocket engine onto Condoleezza's frame of reference here, and so she was moving to the right and getting faster. You might imagine that from her perspective, the cat, in addition to moving upwards, or let me put it this way, the cat would appear to be picking up speed to the left. If her rocket ship was actually picking up speed to the right, then from her point of view, from this set of axes, the cat would look like it was speeding up off to the left. And instead of following this straight line trajectory, it would be curving. And that would look kind of mysterious. So if Condoleezza observed the motion of this cat, which had no no recognizable force acting on it, and the cat was accelerating, as seen from this point of view, then Condoleezza would know that she was actually in an accelerated frame of reference, that she was in a non-inertial frame. So if you see something disobeying the law of inertia, if it's deflecting when there's no observable force or discernible force, you know you are in a non-inertial frame of reference. And if you get that, then you know what we're talking about here. Okay, you could think of Newton's first law as being subsumed by the second, because we know that the second relates force to any acceleration. We've been talking about objects that have no force acting on them, like that cat launched, once it's launched from the cannon, then there's no force on the cat. But what if there is a force? Newton's second law tells you how the acceleration relates to the force. All you need to know is the mass. Let's look at the specific case of zero force. That's the content of Newton's first law, right? If the particle in question has no force acting on it, then the left side of the equation is zero. Well, what's the purpose of an equation? It tells you that this quantity is the same as this quantity. And if we're talking about something like a cat does have mass. So the m is not zero. If the m is not zero, then the only way for the right side of this equation to be zero is for the acceleration to be zero. So no force corresponds to no acceleration. Remember that acceleration, by definition, is the rate of change in time of the velocity. It's the time derivative of velocity. So if something has no force on it, we know that the time derivative of that particle's velocity is zero. Can you put that into simpler terms? What does it mean to have a time derivative of zero? Well, if you think about it conceptually, doesn't that just mean it's not changing in time? In other words, it's a constant in time. Or you could use calculus, integrate both sides with respect to time, pick up a constant of integration. However way you slice it, this says that the velocity is constant. It's really a constant vector. Remember, velocity includes not only how fast you're moving, but the direction in which you move. If your vector velocity is constant, you are moving in a straight line at constant speed. Now, if your speed is zero, then I suppose you're not really moving in a line, you're just sitting there. That would be a special case of constant velocity. But that's exactly what Newton's first law says, right? If a particle has no force acting on it, it will either stay at rest or move in a straight line at constant speed. So we seem to have recovered Newton's first law from the second law for the special case in which the force is zero. And that kind of begs the question, is it really necessary to write down the first law? Can't we just shorten the curriculum by starting with Newton's second law? And that's more of a philosophical question. Some people will say, well, it's important to include the first law, and this may have been why Newton did it. Back in Newton's time, they did not have air hockey tables, baseball games, bowling, airplanes, etc. And so it was really important to emphasize to people that inertia is a real thing, that things will continue in a straight line at constant speed without the need for some force. And nowadays, we include the first law really to define inertial frames. The first law allows us to distinguish between inertial and non-inertial frames. How do you know you're in an inertial frame? If the law of inertia holds. If you're in a reference frame where things are behaving bizarrely, if they're deflecting when there's no readily observable force, then you might be in a non-inertial frame. And we'll look at some examples here. So here's a sequence of some classic, simple demonstrations of the law of inertia. I'll pause for a couple of them and just emphasize how the law applies. Okay, I don't know what this is, a cube of salt maybe. It's at rest, right? It's going to stay at rest unless acted on by a force. So he yanks the ring to the left, but there's not a whole lot of friction that you can develop between the ring and the salt. So if there's no significant force on this cube of salt to the left or the right, then there's no reason it should accelerate. Now, it does fall down, but that's, of course, because there is a force in the downward direction, gravity. Same thing with this one. what's going to happen here? Again, there's no reason this penny should accelerate right or left unless there's a force on it to the right or left. The only way, or the only possible source of that force here would be the friction between the paper and the penny. But the paper is fairly slick, as is the penny. There's really not that much friction, and since he pulls it out quickly, then there's not enough time for what we call an impulse, which is something we'll look at later in the semester. This is even more pronounced. Water has mass. This is significantly more massive than the penny. So to accelerate something with that much more mass, you need a significant force. The only possible source of the force here would be the friction between the paper and the beaker. And there's really not that much friction between a smooth piece of paper and the bottom of the beaker. Those were all examples of, an object at rest tends to stay at rest. This one's different. He's going to get this apple moving, give it a velocity, and then it tends to continue at that velocity until it's acted on by a force. Right? So as he swung the knife down towards the table, the apple acquired the same velocity as his hand. So the apple's already moving. Once the knife hits the table, the apple wants to continue moving in a straight line, and it will do so until it's slowed down by the blade. The chair stops. Why? I mean, the chair's tendency is also to continue moving in a straight line at constant speed. Well, the chair encounters the rather significant contact force with the other chair here. The books, on the other hand, when the chair gets to the other chair, what's to stop the books? The only possible force that could stop the books would be the friction between the bottom book and the seat. But that's not a very large force. These books are fairly massive. That small friction force is not enough to prevent them from continuing in a straight line at constant speed. Of course, when they bash into the wall, that's a different story. Okay, I think you get the idea. Here's a brief clip from a Smarter Everyday video. This one's from several years back. I know a lot of you like to follow this channel, and you can tell how much older this video is because he looks quite a bit younger here. But he went to somewhere in Europe and met up with this group of people that likes, they're slingshot enthusiasts. And here's some nice footage of that's being launched.
Dark red.
Okay, so obviously the sling accelerates the projectile, I'll just call it a ball, up to speed, and then once it separates from the sling, there's no reason it should slow down. It's already moving. It's going to continue moving at a straight line, constant speed. That's the law of inertia. Of course, it'll slow down when it hits a target, or eventually it'll slow down because of air drag, or because gravity brings it back to the Earth. And then it's really the collision with the ground that stops it. Now here's a really nice one that would have been more appropriate in the last video where I talked about F equals ma and Newton's second law. So I'll just interject this here. Great demonstration of the relation between force, mass, and acceleration. So here are two spherical objects with approximately the same diameter, but different, obviously different weights. I think one of these is a ping pong ball. One of them is a solid ball of metal. So what he does, well, you'll see.
This science stuff is very serious. One ball.
So he's about to blow air at these two. Because they have approximately the same diameter, they will experience about the same force. We'll talk more about air drag in the next chapter. But same size and shape means they encounter about the same force. But they obviously have different masses. The more massive one you would expect to pick up speed at a lower rate. So if you think back to the previous presentation and the relationship between force, mass, and acceleration, solve for A. Remember, A is F over m. So if the F is the same between the two, if force is constant, the one with the bigger mass should have the lower acceleration.
One is wooden and the other is brass.
That's a nice demo. Okay, it sounds like that was a wooden ball, not a ping pong ball, but still significantly less massive than the brass ball. Let's move on now to a better visualization of a non-inertial frame. Many of you have heard of the Coriolis Effect. It has a lot to do with weather patterns on a global scale. This is from one of MIT's physics demo videos. There's some great videos coming out of that school. And they've always got their students wearing these white lab coats, even if whatever they're doing has nothing to do with spilling chemicals or anything dangerous. So let's just watch a minute or two of this. See what's happening here? The camera is mounted to the Earth. That's an inertial frame. The camera is not on the rotating platform. And as seen from Earth's perspective, which is the camera view here, when that ball is thrown, you can see it follow a straight line trajectory across the screen. Yes, it's rising and falling due to gravity, but because we're looking down, we can somewhat eliminate that effect. Yeah. Pretty perfect demo, huh? Now the camera is attached to the rotating platform. We are now looking at the trajectory from a non-inertial frame. If you imagine a set of XYZ axes fixed to that platform, those axes are rotating in space. They're not merely moving in a straight line at constant speed. And so we would expect some surprising behavior. Here we saw a ball which was thrown from the person's hands, and if we ignore gravity, yes, gravity is a force that pulls down on the ball. If you ignore gravity, you've got a ball that has essentially no force acting on it. Let's also ignore air drag, and yet it's accelerating. What does it mean if you see a particle accelerating in the absence of force? That's a good way to put it, so let me emphasize that. If you see a particle accelerating in the absence of force, that would be a violation of the law of inertia, or Newton's first law. That would tell you that you are in a non-inertial frame, which we are. The camera is mounted to the rotating platform. Yeah, if you're in a situation like that, your brain's first interpretation would probably be, oh, there's got to be some kind of wind. There's some external force which is pushing on that ball to get it to deflect left. Your first thought is not, I must be in a non-inertial frame. But that's why we're having this discussion. One of the most famous demonstrations of the fact that we actually live in a non-inertial reference frame is the Foucault Pendulum. I believe this is pronounced Foucault, not Foucault. And it's just a pendulum that's fixed to a pivot that's as low friction as possible. And it's a pendulum that's rather long, which means it takes a while to swing back and forth. And if you can really eliminate as much friction as possible at the bearing and hang out for a few hours, you'll notice some interesting behavior. So most Foucault pendulums are not actually built at the North Pole. There's probably no Foucault pendulum at the North Pole because only Santa Claus lives up there. But if you could put a pendulum at the North Pole, this is fun to think about. Get that pendulum swinging and think about the fact that during a 24-hour period, the Earth is going to turn once beneath that pendulum. And there's really no reason that the pendulum should turn with the Earth. The pendulum ought to oscillate independently of the Earth's rotation if the pivot really is frictionless. And there's probably a more precise way to talk about the bearing, but I'll just call it frictionless. The closest Foucault pendulum to you is probably at the Griffith Observatory. I seriously encourage you to go out and check that out sometime if you can. It's probably closed right now because of lockdown. And I love pointing this out. The guy after which the Griffith Observatory is named, that was his last name, Griffith. Do you know what his first name was? It wasn't Billy. It was also Griffith. I think his name was Griffith, or Griffiths, Griffith. That just seems cruel. That's like child abuse, right? You can't name a kid with the same first and last name. Okay, let's watch a little presentation about this from 1960. This educational video is from an era where they seem to have made a lot of amazing videos. Black and white, no CGI, none of the dramatic music that accompanies most educational videos or documentaries now, but they had some truly great props.
Is there any way of telling which is moving, the Earth or the stars? The fact that it is the Earth which is rotating can be demonstrated by means of a pendulum. If I set a pendulum swinging, it swings back and forth in a plane. Now it turns out if this pendulum were at the North Pole of the Earth, the plane of swing would remain fixed relative to the stars, but would rotate relative to the Earth. Now I'll have to show you what I mean. This pendulum is at the center of this turntable, which will represent the Earth. Now I'm going to start the table turning around in this direction. I'll put a black arrow on so that you'll remember. All right, start the rotation. The pendulum is at the North Pole of the Earth, and you are looking at its motion as you ordinarily do, standing on the Earth. The plane of swing rotates in the opposite direction from the rotation of the turntable and at exactly the same rate.
So I hate to interject in such a perfect video, but there again is evidence. If you saw that, that would clue you into the fact that you are anchored in a non-inertial frame of reference, because here is a particle undergoing motion and accelerating in a way that cannot be explained by any observable force. Yes, we know that the tension in the string is causing some of the acceleration. We'll talk about that later. We know that gravity is part of the motion, but why should the plane of the oscillation, see how the bowling ball or whatever this is, it's swinging back and forth in this plane, and then the plane appears to be rotating. And that's not due to any observable force. So if something is accelerating in the absence of forces that would explain that acceleration, you must be in a non-inertial frame of reference. Does that mean that standing here on Earth, we are in a non-inertial frame of reference? We'll take that question up in a moment.
Now look at it from the fixed camera, which will represent the frame of the stars. The turntable, the Earth, rotates, but the plane of the pendulum remains fixed.
So now we're looking at it from a inertial frame. He said the frame of reference of the stars, that's the so-called inertial frame. It was the frame attached to the Earth that was the non-inertial frame.
A pendulum used for this purpose is called a Foucault pendulum. You saw me start one at the beginning of this film. Let's look back again now.
Here is some nice time-lapse footage of a Foucault pendulum. Now, only at the North Pole or South Pole would it actually take the full 24 hours for the plane of oscillation to precess by 360 degrees. At every other latitude, I actually forget if it takes more or less than 24 hours. So this is vastly sped up. You can see the clock off to the left here. So it requires some patience, but if you were to stand there all day, or just watch this video, you've got some pretty direct evidence that we are attached to a non-inertial frame of reference. That would be the rotating Earth. Like I said, you can find one of these at the Griffiths. Now, in that black and white video, Frames of Reference from 1960, you heard the narrator say something to the effect that all motion is relative, so how do we know that it's us that's rotating and not the stars? Most of you are not familiar with this if you have not taken astronomy, but everything you see in the night sky, if observed for long enough, is seen to move across the sky. Things tend to rise in the easterly direction and they set towards the west, and it's a very gradual motion. But if you were to fix your head, let's say you lay down in the grass and held your head really still, 5 or 10 minutes later, you might actually notice that the stars had shifted position. So here's a sped up recording of the so-called diurnal motion of the night sky. Diurnal means daily. If you'd like to know a number, it takes about 4 minutes for the stars to move through 1 degree. Take your pinky finger, hold it out at arm's length at night, and the width of your pinky at that distance from your face is about 1 degree. So you would have to wait 4 minutes for the stars to cross your pinky. Pretty slow, which is why you tend not to notice it. But that motion is due to the Earth's rotation.
This portion brought to you today by Dawn, the dishwashing liquid that takes grease out of your way, and by Bold 3 detergent with built-in fabric softener.
What a great theme song. You know, looking back at that intro to a soap opera from, I think it said 1986, I'm not sure which is more impressive, the advances in car technology, for instance. We've got the self-driving cars, or the advances in marketing, because you look at the print on that box of detergent or whatever it was. It looked real primitive compared to today's advertising. Okay, are we attached to a non-inertial frame? I think it's fairly evident at this point that we are. So how come we don't normally notice that? You know, if you go out and throw a tennis ball, it sure looks like it's making the parabola that you would expect it to make if gravity were the only force. And yet we've just seen that if you're in a non-inertial frame of reference, you should observe acceleration that has no explainable force. Like there should be acceleration in the absence of identifiable forces. How come we don't see that when we throw a basketball or a baseball? Well, just to convince you that that the reference frame that you're working with is non-inertial, I've pulled up Google Earth on the web here, drawn some axes attached to a particular point on the Earth, in the middle of the ocean evidently, and let's just watch what happens to those axes as they turn with the Earth, as the world turns. Now the z-axis is poking out of the page there, and now the x-axis is kind of going into the page the opposite direction. Let me do that again. So with each slide, I'm turning the Earth through, what is that, 90 degrees? So you can see a couple things going on here. This is not obvious, maybe the first time you think about it. The coordinate system is turning. Do you see how the direction of the z-axis is changing? First it's pointing off to the left, then it's pointing out of the page, then it's pointing off to the right. You can say something similar for the x-axis. So not only is the coordinate system itself, or the axes, rotating, but their origin, their common origin, is also accelerating. Because look at the origin. It's describing a circle. It's attached to the equator. It's describing a circle through space. And we know that something moving in a circle is accelerating. It's got a centripetal acceleration. So this is definitely an accelerated reference frame. It's non-inertial. If you're talking about an inertial frame, you're talking about a set of three axes, that's how you can think about it, that are moving through space in a constant direction at constant speed, and they're not rotating. And this violates two of those conditions. Yeah, we already looked at that. So there are scenarios in which the Coriolis acceleration is observable, not in everyday life, but here's an interesting thought experiment. Let's go back to the Burj Khalifa, but before I get to that, here's planet Earth, and we're looking at it from above the North Pole. I believe I Googled an actual image here. This was the first image taken from above Earth's North Pole, and yeah, so just to remind you of that, there's Santa's little house there. And let's just pretend that the Burj Khalifa is near the equator. I'm pretty sure it's north of the equator. And this is obviously not to scale, because even Mount Everest evidently can't even be seen from outer space. It's barely even a pimple on the surface of the Earth. And here's Shakira standing next to the Burj Khalifa. But don't forget that the whole planet is turning. It's rotating counterclockwise as seen from this vantage point. And now imagine that we drop something from the top of the Burj Khalifa. Let's not worry about air drag, pretend there's no atmosphere, and Shakira's got a face mask on, or an oxygen tank. What should we drop? A grenade, a quarter? Let's zoom in. I'll go with a cat. Let's drop a cat from the top of the Burj Khalifa. And this is the question to ponder. Is this cat going to fall straight down, as seen by Shakira, or will it drift to the left or drift to the right? Because remember, everything's turning. The whole planet is turning. That includes the Burj Khalifa, which is attached to the planet. That includes Shakira, who is attached to the planet. So will the cat do something like this? Let me back up. Imagine the whole thing rotating counterclockwise. But since the cat is not actually fixed to the planet, the cat would be in free fall. Maybe the cat will fall straight down, but since the Burj Khalifa and Shakira continue on to the left, it would appear that the cat drifted right. You feel me? What would it look like from Shakira's point of view? Because if you're anything like me, this was my first guess when the first time I thought about this. If the cat just falls straight down while the Burj Khalifa and Shakira are rotating counterclockwise, then from their point of view, it should look like the cat had drifted off to the right, which would actually be west, in the westerly direction. Is that what in fact happens? Well, I'm pretty sure that this has been checked many times. It's difficult to, you would probably need an evacuated chamber, like a really tall tube with the air sucked out to really observe this behavior. It's easy to calculate this behavior, but what actually happens is the opposite, surprisingly enough. And here's how you can understand that. Let's draw some circles here. So this circle shows basically the path taken by Shakira's center of mass. If you imagine the center of mass is somewhere along the midline of her body, it's going to move around this circle as the Earth rotates. But because the cat is at the top of the Burj Khalifa, the cat would be tracing out a much larger circle, well, somewhat larger circle before the cat is dropped. And this whole system is rigid. Everything has to turn together, right? It's not like the crust of the Earth turns at a lower rate in radians per second than the top of the Burj Khalifa. Everything is rigid. And if that's the case, you can use this equation. I probably should have written V tangential here. But remember, for a rigid object rotating with angular velocity omega, that's the number of radians per second, it's got to be radians per second if you want to use this equation, then the farther out you are from the center of the circle, the faster you're moving tangentially through space. We say that the tangential speed, that's in meters per second, is proportional to your distance from the center. And the constant of proportionality is the angular velocity. This is an equation you'll be using many times this semester. So since the kitty cat is farther from the center of the Earth than is Shakira, the cat would actually have a greater tangential speed, as I've indicated with the longer arrow here. And that may help you understand why the cat actually drifts the opposite direction as seen by Shakira. Because you have to imagine, as the cat's falling, the cat continues to move in its tangential direction. There's no reason why the velocity the cat has in this direction should just suddenly disappear. So during the fall, the cat maintains its sideways motion while acquiring a downward motion. And you can see that it would trace out an arc, something like that. And because the cat initially was moving faster in the sideways direction than was Shakira, it will overtake Shakira and the Burj Khalifa and end up on this side. So that's actually what you would observe. Contrary to what you might expect, instead of the cat drifting to the west on the equator, as one might expect, the cat will actually drift in the easterly direction or eastward direction as it falls. That's a surprising consequence of being attached to a non-inertial reference frame. And that's often called the Coriolis effect. That's one manifestation of the Coriolis effect. Often when you hear about the Coriolis effect, it's in the context of meteorology, global weather patterns. And I think I have a graphic for that. Yeah, you may have heard that hurricanes or cyclones, they turn one way in the northern hemisphere and they turn the opposite direction in the southern hemisphere, which is pretty remarkable behavior. And you can only explain it with reference to the Earth's rotation. You need the physics of non-inertial reference frames in order to explain that fact, that storms turn different directions in the two hemispheres. You may have even heard that when you flush a toilet in the northern hemisphere, the water swirls the opposite direction from the direction that it would swirl in the southern hemisphere. That has been debunked. There are other factors at play in flushing toilet water that are more significant than the Coriolis acceleration, but you can check out a collaboration video between the Smarter Everyday guy and the Veritasium guy, or Veritasium as I think he calls it, and they actually investigate this hypothesis using a large child's pool. You know, you can just fill them up with a hose. They set one of those up in the two hemispheres and drain it to see which direction the water swirls, and I believe it swirls opposite directions in the two hemispheres. They did a really good job of setting that up in a controlled fashion. So check that out if you're curious. And lastly, I was surprised to find a video on YouTube where a guy talks about the need to take into account the Coriolis acceleration when firing a rifle over long ranges. I knew that in ballistics, this is important. You know, if you're going to send a missile halfway across the world, you absolutely have to take into account the rotating of the Earth in order to strike your intended target. I didn't realize that it would be important even at 1,000 yards. And before I hit play here, I will also interject. You can find a video with Neil deGrasse Tyson talking about whether the Coriolis effect would be important in a touchdown kick in football. Like if a football barely misses the field goal by just an inch, could that be attributed to Coriolis acceleration? I forget the answer, but you can look that up if you'd like as well.
Now, real quick, let's kind of just explain the Coriolis effect in layman's terms. The Coriolis effect is the effect that when the bullet leaves the barrel of the gun, it is actually leaving the surface of the Earth. So as the bullet leaves the barrel of the gun, the Earth is still rotating, and the bullet is not rotating with the Earth. So the Earth will actually rotate out from underneath of the bullet while it is in flight. So as the Earth rotates, it actually rotates from the west to the east. So what that's going to do to our targets is if you're shooting west, your target's going to rotate up and towards us, which is going to cause the bullets to hit lower. And if you're facing east, the target's going to be dropping and slightly moving away, which is going to cause the hits to be higher. Now, Why this is important is out to 1,000 yards, you could have almost a full minute of correction due to Coriolis effect. Depending
Okay,
on
sorry about
which
that. My
direct-
connection's getting weird. And let me point out that you do not need to understand these details or remember them. The real takeaway here is about it's just about the difference between an inertial and a non-inertial reference frame. Let's see the proof of what this guy's talking about.
All right, we've made it down to our target that we shot at the west. This is our west target here. And as you can see, they've all dropped in quite low. We've got 8 inches from center to the center of the group, which is a little lower than we expected, but we were dealing with some pretty stiff mirage. So we got a nice little group here. We're gonna pack up this target and head down to our target that we shot to the east, and we'll compare the two groups and show you the difference of just switching directions. That's all we did. We switched from west to east. All right, we've made it down to our target on the east target now. And as you can see, they're not quite too high. We've got about 3 inches, maybe 3.5 to the center of the group above bullseye. So if we compare this to our other target, we're 3 inches high here, we're 8 inches low there. That's 11 inches, just over a minute of difference between just shooting from the west to the east. Now, how does it?
So he's talking about a minute of arc. That's 1/60th of a degree. So there you have it. This guy understands better than the vast majority of people that we are living on a non-inertial reference frame. What was I going to add to that? Yeah, for him, it's just common sense. For the rest of us, we're blissfully unaware. So you don't need to understand any of the numbers or remember any of the numbers he just threw out. You just need to understand the difference between the two types of reference frame. How do you know you're in an inertial reference frame? If you see the law of inertia holding true. If you are observing particles accelerating without identifiable forces, that clues you into the fact that you are in a non-inertial reference frame. Cheers.